Hello everyone. A very good afternoon to one and all. So today we're gonna start with my research topic, which is lattice-based post-quantum cryptography by the students of Texas A&M University. We both are pursuing masters in computer science. My name is Akil Chandra Gorkala, and
I'm
I'm
Saireshma Potturi.
sorry. You can go ahead, Reshma.
I'm Saireshma Potturi.
Yeah, okay. So coming to the overview. Yes, Reshma.
So today in this presentation, we are gonna discuss about the introduction, problem analysis, literature review, and what are all the references we took while doing this paper.
So coming to the introduction. So before giving a brief introduction about a paper, I would like you all to know about the cryptography. So cryptography, which is also known as cryptology, which is a practice of encrypting information as that only intended recipient can read it. So coming to our paper, which is lattice-based cryptography, is a type of cryptography that uses lattices to uh, lattices to perform the cryptographic functions and security prospects. So coming to post-quantum security, the quantum here, the word indicates the quantum in physics, where quantum physics lattice is represented as a regular uh, repeated three-dimensional atoms, ions, and molecules, which are metal or other cryptolic solid substances. So coming to our paper, the hash functions and its security for snags is my previous paper. This is the continuation for one of the paper two. And coming to my paper's introduction personally, so as we stand on the cusp of new technology era, the threat of quantum computers looms large. So these powerful machines, capable of breaking many of today's cryptographic algorithms, necessitize a paradigmic shift in our approach to cybersecurity. One promising solution lies in lattice-based cryptography. So now we can imagine a multidimensional space filled up with points arranged in a precise pattern. The structure, the structure known as lattice forms a foundation of lattice-based cryptographic systems. Yeah. So, the beauty of this lattice-based cryptography lies in its resistance to quantum attacks. While quantum computers excel at a certain task, they struggle to solve problems related to lattice structures. This inherent difficulty problems related to lattice structures. So, this inherent difficult problems for the security aspects too, or foundation for cryptographic primitives like encryption, digital signatures, and message authentication codes.
In recent years, researchers have made significant strides in improving the efficiency and practicality of lattice-based schemes. This progress brings us closer to a world where we can confidently protect our sensitive data from the quantum threat. By embracing lattice-based cryptography, we can safeguard our digital future and ensure a secure and resilient cyberspace.
Yeah. Coming to the next slide, which are the problems and the problem analysis, which we have done related to the post-quantum cryptography. Here we have four subtopics like learning with errors, the public key crypto system using learning with errors, and the short integrated solutions, also known as SIS, and finally the dual crypto system.
Uh, so from the last four problems, we are going to discuss mainly on the LWE and SIS, that is learning with errors and short integer solutions and dual crypto system. So coming to the learning with errors, this slide introduces the learning with errors problem, which forms the basis of many lattice-based cryptographic schemes. So in this learning with errors, there are four key points: search LWE, decision LWE, hardness, and public key crypto system. In the search LWE, which is given a matrix A and vector A and B, the goal is to find a vector S such that B is approximately equal to the product of A and S plus some noise. In decision LW, the goal is to distinguish between a pair A and B generated according to the LW distribution and a uniformly random pair. Coming to hardness, both search LW and decision LW are believed to be computationally hard problems, even for quantum computers. Public key crypto systems. In this one, Regiv's public key crypto system is based on the hardness of decision LW mainly. The public key is A, the secret key is S, and the encryption and decryption involve matrix operations and noise addition. In essence, LW problems involve finding patterns in noisy data, which is a challenging task for both classical and quantum computers.
Yeah. So now coming to short integer solutions. So in this slide, this introduced the short integer solutions, the sys problems, and other fundamental problems in lattice-based cryptography. So here, given a matrix A, the goal is to find a non-zero integer vector x with a small entries such as ax is congruent to 0 modulo q. So in lattice perspective, the sys problem can be viewed as finding a short vector in the lattice C of A, which is the set of all integer vectors that satisfy ax, which equals to 0 modulo q. One-way hash function, the sys problem can be used to construct a one-way hash function. The function maps a binary input x to the vector ax modulo q. The hardness of the sys problem ensures I'm sorry. So yeah, the hardness of the sys problem ensures that it is computationally difficult to find two different inputs that hash to the same output. In essence, the sys problem involves finding a solution to a linear equation which constrains on the size of solution. This problem is believed to be computationally hard even for quantum computers. And now coming to dual crypto systems, this slides represents a dual crypto system based on LWE, which means learning with errors problems. So here the public key, as the previous LWE based crypto systems, the public key is matrix A itself, and the secret keys where Alice and Bob both have a secret keys. Alice has X and Bob has S. Coming to encryption, so the Bob generates two ciphertexts, which is B power T equals to S power T of A plus E power T, where B dash or B hash equals to S power T U plus E hash plus bit of Q by 2. The second ciphertext is modified by adding a term bit of Q by 2, where bit is a binary value. And coming to the decryption, Alice can recover the bit value by computing b dash minus b of t x b dash minus b of t x. So if the result is approximately q by 2, then bit is 1, otherwise it is 0. The key idea behind this dual crypto system is that the modification to the second ciphertext does not affect the LWE distribution, which is learning with error distribution. This allows Alice to recover the bit value while preserving the security of the lattice-based LWE, which is learning with errors based encryption scheme.
So coming to the literature review, the background of the paper is lattice-based cryptography is rapidly evolving field with significant progress made in recent years. Researchers have developed efficient implementations and improved the security analysis of various lattice-based schemes. As the quantum computing technology continues to advance nowadays, lattice-based cryptography will likely play a crucial role in ensuring the security of our digital infrastructure. Its resistance to quantum attacks makes it a promising candidate for post-quantum cryptography.
So coming to the references, we have few references taken out from internet, from Google Scholar and many other stuff. Like we use some cryptographic hardware and embedded systems, a decade of lattice cryptography by University D, Padova University D, and LWE based, like better key sizes for LWE based encryption and introduction to post quantum cryptography and so on. So these are the references which we used. These are some more references which we used. And finally, thank you so much for taking your time and looking into our presentation. This is
Thank
a
you for
yeah.
thank you.